Okay, it's great to be here. 80-degree weather, which is a treat in January, is for someone coming from Urbana, Illinois. So, anyway, so this is joint work with one of my PhD students who's just finishing up, actually, Taposh Banerjee. So, how many of you have heard of the quickest change detection problem or quickest detection problem? Heard something? Okay.
That's about it.
You've just heard about it. Okay. The first part of the talk will be an overview or a review of a quickest change detection, and then I'll talk about what that first term I have there, which is data efficient. That's the new thing. Okay. All right. So here's the quickest change detection problem. You have a sequence of observations, right? And the distribution of the observations changes at some point, some unknown point in time gamma. Okay. And so here in the simplest model, for example, the distribution of observation could be IID with some PDF F0 before the change occurs and after the change is there, IID F1. Okay? And the goal here is to stop it at some point in time and then declare that the change has happened. And you want to declare the change has happened after it happened. So there's a trade-off, because if you're too aggressive about declaring the change, you might declare it too early and incur a false alarm. So the trade-off between detection delay and false alarms. And the goal is to find a test that gives you a good trade-off between these two quantities. That's the quick change detection problem. So the original application goes back to maybe about 60 or 70 years, I guess, when the quick exchange detection was used in quality control in manufacturing systems. So think of maybe making paper clips or something in a large, in a factory, and you test these batches of paper clips, and then if, based on the percentage of clips that are coming out incorrectly or with some defects, you then declare that there's something wrong with the manufacturing process and stop the process and reset things. Okay. Other applications, more recently, people are talking about using these techniques for infrastructure monitoring, like for putting sensors on bridges and using those sensors to determine if there's going to be some catastrophic failure on the bridge in the near future, using stress measurements and so on. Okay. You could also use it in power systems, maybe to predict impending failure and cascading failures or something like that. You could use it for environmental monitoring, of course, to detect changes in, say, an abrupt increase in pollution level and tell people to stop driving their cars as much. And there was a cool application, actually, one of my former colleagues who left about the same time that Sean did, Todd Coleman, was working on trying to use these ideas to detect the onset of epilepsy using sensors placed on the brain. Okay, so to actually predict when you might have an attack before it happens. Okay. So here's a simulation that might illustrate what quickest change detection is all about. So here's a sequence of samples. At some point, the sequence goes from being Gaussian with zero mean and variance 1 to Gaussian with variance 1 and a slight increase in mean to 0.1. Okay, and if you look at the sequence, you can't tell that anything has changed. Okay, but it turns out actually things do change. The distribution actually changed at time 500. Now you want to see if you can devise some kind of detection scheme that can detect that this slight change in distribution has happened, again, as quickly as possible. Okay, and it turns out there's a very nice test, and what I'm going to show you is the evolution of the statistic of the test before and after the change. Okay, so this is the test, and I'll talk about this in a little more detail in the next couple of slides. But this is called the Shearer algorithm. Okay, and there's some statistic it's computing on the y-axis, and before the change, you'll see before time 500. The statistic hovers around 0, and after 500, it starts to take off. Okay, so it's doing the right thing. If you wait long enough, you wait till it's large enough, crosses this threshold of 0.8, and declare a change, then you would get a pretty good trade-off between a pretty small false alarm rate. You incur a delay, in this case about 500 samples before you declare the change. Okay, but so you want tests that do this, and I'll talk about how you construct such tests. Okay? And remember, this is different from a standard detection problem, because in a standard hypothesis testing problem, the observations either come from one distribution or the other. Okay, and here it's like things are changing at some point. Okay, so the way you construct tests is going to be quite different. So this test was proposed, actually, I'll talk about the Bayesian setting first, and although historically the non-Bayesian version came first. So what's the Bayesian setting? In the Bayesian setting, you assume that the change has a known prior distribution. So you give it a random model. So the change point gamma is now denoted by a capital letter gamma, which has a geometric distribution with some parameter rho. And why geometric? Again, this is a standard model for characterizing hazards and so on. It's a memoryless distribution. That's the main reason for using it. Okay, and also I'll talk a little bit about what you might do if you don't have a very good prior. In which case, if you make the rho small, it turns out to basically assuming that you don't have a prior, or uniformizing the prior. Okay, so we need to characterize, we need to quantify rather delay and false alarm, right, and then trade them off. So delay can be measured by looking at the difference between when you stop, tau, and when the change happened, gamma, and the positive part of that. Okay, that's okay. So, and the expected value of that quantity we'll call ADD, or average detection delay. False alarms are characterized by the probability that you stop before the change happens. Okay, and you want a good trade-off between these two. You want to minimize delay subject to a constraint of the false alarm. Right? And the solution to this actually can be found, and in fact, Sherev's original solution was basically a dynamic programming-based solution. And you look at the sufficient statistic for this problem is the posterior probability that the change happened before time n, given the observations up to time n. Okay, that's all you need to keep at time n to make a decision about the change. If this is large, that means it's quite likely that the change has already happened. Okay, and you can see that actually that has a simple recursion. This posterior probability has this recursion, and this quantity here. Now you see that this recursion has this likelihood ratio sitting in it, right? So again, the likelihood ratio, since you're trying to distinguish between two distributions, the likelihood ratio between them should play a role, and it does. Okay, and so you wait. The first time it crosses some large value A, you say changes happen, and you choose the threshold A to meet your false alarm constraint. So if you do that, then this test is actually optimal for that constraint optimization problem. Okay, and here's a typical evolution of the statistic, and we saw a picture similar to this before. So if this is actually what happened, this is a case where rho was 0.01, and this is Gaussian observations with different mean before and after change, and a threshold of 0.99 in this case. And you see that, and the change happens at time 100 here. And you see that you could have paths where you cross this threshold before the change. That's a false alarm path, and this is a delay path. Okay.
How did you get the blue curve? You just ran that. You kept running.
Just simulations, and you found one that was a false alarm path, yeah. Another one that was a delay path. So that's a typical evolution. So basically, before the change, things it'll tend to hover around 0, the way the statistic operates, and it's because likelihood ratio here is going to be small before the change, right? And then it's going to be large, bigger than 1 after the change. And so this posterior probability will stay around 0 before the change, and after the change it starts to take off. So actually, interestingly, this test was developed in the 60s, and there wasn't any performance analysis of this test until 40, more than 40 years later, I guess. This is something that one of my collaborators, Tartakovsky and Alex Tartakovsky and I did in 2005. So basically, how do you actually, given parameters of the test, in this case the threshold, can you say something about the delay and false alarm performance? And typically you want to know how false alarm and delay are related, right? So you can easily bound the false alarm probability. That this is not that hard to do, but the more interesting result is that the delay versus false alarm actually has this relationship, that the delay goes as the log of the false alarm probability, and there's a slope that's determined by both the prior rho as well as the KL divergence between the distributions F1 and F0, right? And you expect the KL divergence to play a role because this is after all, a detection problem. And you'll also notice that this relationship between false alarm probability and delay is an exponential relationship. So you can think of this quantity here as a kind of error exponent for this sequential detection problem. Okay? So the KL divergence is actually the error exponent for this problem. Okay? But you also see that you see the rho of the prior versus the KL divergence in this equation. So if rho is small, and you take rho to 0, then the prior plays a smaller and smaller role, and you're relying more on the observations, and vice versa. If rho is large, you rely more on the prior. Okay? But this tells you exactly how the distributions and the prior on the change point play a role in this trade-off between delay and false alarm. And actually, the tools that you need to use to do this analysis come from the area of nonlinear renewal theory. And what's meant by nonlinear renewal theory is you basically you're looking at a statistic crossing a threshold. So renewal theory actually talks about how to characterize overshoots when you have a random walk crossing a threshold. That's one of the purposes of renewal theory. And what happens in this case is that you don't quite have a random walk. You have random walk plus some so-called drifting term. And you need to characterize what happens when this random walk plus a drift crosses a threshold. And that's the topic of nonlinear renewal theory. And you can use that to actually derive this relationship. Okay? And in fact, if you plot in simulations, if you plot the delay versus false alarm probability, you do get this linear relationship between delay and false alarm. And the slope indeed corresponds to what we have in the theory there. Okay? So that's the Bayesian setting. So what happens if you don't have a prior on the change point? Right? So there are a couple of formulations of the problem. In fact, there was a test that was proposed in the 50s before anyone actually formally posed this as an optimization problem. Okay? So we'll talk about that later. But we'll talk about Lorden's formulation of the problem. So you don't have a prior now on the change point, so I'll use the lowercase gamma here. So in Lorden's formulation, he characterized delay using this somewhat pessimistic or kind of a worst case delay, right? So you look at, so it says, let me explain some notation here. This E sub n denotes the expectation when the change happens at time n. So we have this observation sequence. You condition on the change having happened at time n. Look at the delay, and then condition that on all the past observations before time n. Okay, now you have something that's a random variable. You take its essential supremum, and then take the worst case value of n, and that's the worst delay that you can have. So that's how you characterize delay. Okay. There's another way to do it, which I'll talk about in just a second. Okay. And then you characterize false alarms through what's called the false alarm rate. And this is so the E infinity here stands for the expected time it takes to stop when the change happens at infinity, in which case all the observations actually come from the F0 distribution, okay, or the pre-change distribution. So you can imagine having observations that all come from the pre-change distribution, and you stop because of a false alarm, right? and you stop, you reset the system, and then start taking observations again. So the rate at which you do this stopping is the inverse of this quantity, and that's called the false alarm rate. So that measures that's our measure of false alarms. And you want to minimize the delay subject to a false alarm constraint. Okay? Now, there was another formulation due to Pollock in the mid-1980s, and he decided to make the delay expression a little simpler. So rather than taking this essential supreme by conditioning on the observations, he just conditioned on the event that you stop after time n, okay, and just takes the supremum that over n, and you can actually show that this CADD is always going to be smaller than WADD. That's not that hard to show. Okay, and then again you can pose the problem as an optimization of CADD versus FAR. Now it turns out that a good solution to both of these problems is a test that was proposed by Page in 1954 called the cumulative sum test, or the Q-sum test. So what's the Q-sum test? It's actually it's very easy to think of it as just a maximum likelihood ratio based test. Okay, so if you look at the likelihood of the observations that there was no change at time n, right? They'll all come from f0, so it'll be the log of that likelihood function. If the change happens at some time k before n, then the pre-change observations have likelihood function f0, post-change f1, and the log of that is the likelihood function for change having happened at time k. And so basically what you do is you form a statistic which is like you're pretending like you're finding the maximum likelihood estimate of the change point, okay? And one of the possibilities for the maximum likelihood estimate is that the change happened after time n. That's why I've included n plus 1 here, okay? Now you've got this likelihood function. If you actually wanted to determine what the change point was, given that, so suppose someone told you at time n, the change has happened sometime between 1 and n, okay? Find the maximum likelihood estimate of the change point, you just choose the value of k that maximizes this between 1 and n. So what Page said was, well, if this likelihood function is large for some value between 1 and n, right, then it's very likely that the change has already happened before time n. Okay? So you can use that as a way to determine when to stop. So if this maximum likelihood statistic is large, then you stop and say a change has happened.
Is F0 and F1 part of the problem data? Do you know what F0
Yes, yes, but right now I'm assuming you know F0 and F1, but there are variants of all this. There's a lot of work that I'll briefly mention that. Right. So it turns out that you can write this maximum likelihood statistic using a recursion, a nice recursion. And this people who've studied queuing models, this looks a lot like a queue, right? GT1Q or whatever, with the arbitrary input process, and the queue length has to always be positive, and the statistic actually always remains positive. Okay, so in fact, if you plot the evolution of the Q-sum statistic, what happens is before the change, it tends to hover around 0. So it actually goes up a little bit, maybe come down and get zeroed out, because when this quantity, if the log likelihood ratio goes way negative, right, because you're in the pre-change mode, that's likely to happen, then you're going to end up with a Wn plus the log likelihood, which is a negative number. So you take the positive part, it gets zeroed out. So basically, there's a lot of visits to 0 before the change, and after the change, it starts to take off. Okay, so that's yeah, exactly. Yeah, that's a good way to think about it. Yeah. Okay. In fact, you can show that this test is exactly optimal under Lauden's minimax criterion, and that was a very interesting proof given by Mustakides in 1986. which is a very difficult paper to read, by the way, if anyone wants to read that. But Lai has a much more elegant paper, actually, about the optimality of the Q-sum, and he actually shows that it's asymptotically optimal as the false alarm rate goes to 0 under Pollack's criterion. So it's actually, this test is good, really, under both criteria. It's good for the case where you don't know the distribution of the change. Point. What about asymptotic performance? So again, if you look at the Q-sum, I'm only going to talk about the Q-sum test. There are other tests, by the way, you can develop, which are also asymptotically optimal. And they have in some cases, better properties. But let's focus on the Q-sum test. So if you look at the false alarm rate of the Q-sum test, you can easily show that if you set the threshold above which you declare change to equal the magnitude of the log of the false alarm, the constraint, then you meet the constraint. Okay, that's a very easy way to meet the constraint in this case. And as this false alarm rate goes to 0, again, I didn't mention this before, why are we interested in the situation when the false alarm rates go to 0? That's basically, in practice, that's what you'd be interested in, right? You want low false alarm rates. You may be willing to take a bit of a delay for that, but you really want to operate with low false alarm rates. Okay, and so you get this, again, this exponential relationship between false alarm rate and delay, okay, where the error exponent is the KL divergence. You don't have the log rho term here because there's no prior in this case. And the same thing, you plot it in simulations, even when you're operating at false alarms that are not very small, you get a straight line.
I can't tell. Does it hit 0 or does it?
Well, that is, as the false alarm rate,
There's a big constant.
there's a large constant here. You get the slope right. Yeah, in fact, the constant can also be worked out. So what I've talked about here is first order asymptotics, where the ratio of these two quantities is going to 1 as false alarm rate goes to 0. If you want higher order asymptotics, you can do it in the IID case. Interestingly, this result actually generalizes very nicely to when you don't have to have IID observations before and after the change. This gets replaced by something that's similar to the KL divergence. Exactly. Yeah. So you can do all of that, but you can get higher order results for the IID setting. So you get something that says that the delay is log false alarm divided by KL divergence plus some constant, and so you can actually nail down that constant plus little o1. Okay, so now let's talk about the data efficient setting. So that was just a review of quickest change detection in general. So this is the new stuff. So suppose there's a cost associated with acquiring the observations, and it might be so in process control, for example, in manufacturing settings, there's a cost associated with testing batches, right? So each time you get an observation, you need to stop something to make that happen. Or if you're talking about some other setting where you're testing patients or something for diseases, again, the expense associated with that. Or if you're talking about collecting data through a sensor network, the cost of acquiring observations might be the energy that's consumed, not just in acquiring the observations, but maybe transmitting it to some other location. Okay? So typically in practical applications, there's this cost associated with acquiring observations, which is ignored in the original setting, because all you care about there is false alarms and delay. Okay? Indirectly, you're penalizing observations taken after the change through the delay, but that's kind of an indirect cost of observations. Okay, so in the data efficient setting, we allow for 3 possibilities instead of just 2. All right, in the standard setting, you either stop and make a decision or continue and take the next observation. So we have the option of continuing without taking the next observation. Okay, might skip an observation. And so we have this additional control variable, and if this control variable s takes the value 1 at time k, you use xk for decision making. Otherwise, you don't use it. Okay? So now, as you collect observations, and you're skipping some of them, the information that you collect that's useful for decision making at time k, okay, is actually, this is all the information, tells you which observations you have skipped, and the superscripts, if it takes the value 0, there's a null there. If it takes the value 1, I get that observations. So this information vector ik contains actually all the observations that were actually used and which ones were skipped. Okay, so that's the information you have at time k for decision making now. And so a policy that's data efficient has to pick a stopping time on this information sequence, as well as the control. The control at time k can be a function of the past information vector, okay, which tells you whether or not to take the next observation. And now, instead of just a stopping time tau characterizing the test, you have the stopping time tau and all these policies for skipping or taking observations, mu1 through mu tau. And together they form this policy phi. Okay? Okay, I think I've already said this. Okay, so now let's actually talk about a formulation of data efficient quick exchange detection in the Bayesian setting first. So we basically extend Scherer's formulation essentially. Again, we'll assume that we have a prior and the change point, which is geometric. Now, in addition to the delay and false alarm probability, we have another metric that measures how efficient we are in using our data. Okay, and we're going to basically count the expected number of observations that we take before the change point. Okay, why are we only penalizing observations before the change point? Well, after the change point, you're actually already kind of penalizing the observations because through the delay. The other thing is, after the change happens, you really want to be taking as many observations as possible, right, to quickly make a decision about the change. But before the change happens, right, you're wasting observations, right, when you're operating under the null hypothesis. So you want to really keep that to a minimum, the pre-change distribution. Okay, so the A and O stands for the average number of observations used before the change. Okay, and so you want to minimize the delay subject to a false alarm constraint, as well as a constraint on the number of observations that you take before the change. Okay. And before I talk about this optimization problem in more detail, let's just look at a test that might do something like this. A very simple test, a simple modification of Scherer test. So we call this the DE Scherer test, data efficient Scherer. So Scherer test basically has this one threshold A, which if the posterior probability of the change exceeds that threshold, you say that change has happened. So we add another threshold, B, and if you're below this threshold, if the statistic is below the threshold, we skip observations. As simple as that. That's all this test is. Okay? So that's all that's happening here. Again, you declare the change when the posterior probability is larger than A, just like before. But you notice what's happening below B. So below B, if you skip an observation, so what should you do then to update your belief about the change? Well, you use the prior. And when you use the prior, it turns out that you have this linear increase in P. And that's not that hard to see. Actually, write down the equations. If you update using the prior, you actually increase the posterior probability in this linear manner. Okay? And if you use an observation, you have the same old equation we had before that uses the likelihood ratio. Okay? So that's a test. And yes, here's again a more detailed description of the evolution of the test. when you're below B, in this case, it so happened that I started the statistic at 0. I could have started the statistic at time 0 at the threshold B. Okay, and then, so you wait till you cross the threshold B, take an observation. If it takes you up, you will start taking more observations. Anytime you fall below the threshold, you start using the priori again to get out. Okay. So you can actually pose this again as a dynamic programming problem, and you can actually justify you can justify this test as a solution to basically a Lagrangian version of the constraint optimization problem. Okay, but it turns out actually that it's a little more complicated than that. If you actually solve this optimization problem, minimizing a linear combination of delay, false alarm, and ANO, okay, it turns out that the test doesn't have this two-threshold structure. In fact, you can show that in general, you could have multiple thresholds. Okay, and the reason for multiple thresholds is because actually decision regions for this test are determined by the intersection of two concave functions, and they can intersect in many different places. That's the problem. But it turns out if you compute this thing numerically for given values of the constraints, right, then most of the time you get a two-threshold solution like the one I described. Okay. But that was just the one way to justify the test. Actually, a much nicer way to justify the test that we have is to look at the asymptotic setting again. Again, we're interested in low false alarm, so we'll let alpha go to 0. We're going to fix beta, and you can show that if you do that, as alpha goes to 0, then the false alarm rate achieved by a data efficient test is up to first order the same as the Shearer test, which does not skip observations. And the delay also is up to the first order the same. So this test actually you can show is asymptotically first order optimal. Okay? And in numerical results, you can show that you can get a very nice gain in data efficiency over the Shearer test. The other nice things about this test is that you can actually do an analysis, and which I haven't included here because it's a little messy. You can actually set these thresholds independent of each other. With the threshold, a larger threshold, you can imagine can be used to control false alarms, and the lower threshold can be used to control the average number of observations. And you can actually get nice expressions for these things and use those to set those thresholds to meet certain constraints. Okay. But here are some results that show how this test performs. These are trade-off curves for delay versus false alarm rate for different values of constraint on ANO. So that ANO 75% means that I'm using 75% of the observations that the Shearer test would use to achieve the same false alarm rate. Okay, so you do get a little bit of increase in delay for a given false alarm over the Shearer test that uses all the observations, but only a slight increase in delay to gain quite a bit in data efficiency. So you could go up to 50% of the observation, skip every other observation, and you incur a little more delay. Okay, but we know that this asymptotically first order optimal. So actually, the slope of these lines is the same as the Shearer test. Okay, only the constant changes. Okay, now what should we compare this with? So a naive way to save energy, right, or to save observations, is to just skip observations randomly, right? So if I want to achieve data efficiency of 50%, I just skip half the samples. So if I did that and then plotted the trade-off curve that I get, okay, I'm a lot worse than what I would get using my test. So basically, using the statistic to tell you whether or not to skip the observation can be can give you a huge gain in data efficiency. Okay, does that make sense? All right. So what happens in the Minimax setting? So it turns out the Minimax setting is a little more complicated. and we'll see why. So we don't have a prior on the change point. Okay, and we want to extend the formulations we had for the non-data efficient setting to the data efficient setting. So first of all, we need a metric to capture the cost of observations, and it's not obvious how you capture this cost. There's no easy way to look at the average number of observations used before the change point. The other thing is, the more important thing is, what do we do when we skip observations, right? In the Bayesian setting, it's nice, when you skip observations, you can still use the prior. Okay, the prior tells you something about how likely the changes, how likely it is that the changes happen. Okay, so what we did in this case was to take the test from the Bayesian setting and basically translate it into the Minimax setting, and then prove that that test is asymptotically optimal in the Minimax setting. Okay. So first, let's look at so this is the Bayesian setting. So we had this metric of data efficiency, right? So we need a new metric now that doesn't involve this prior on gamma. Okay. So what we're going to do is use this quantity, which I'll call the pre-change duty cycle. So think of the duty cycle as basically, think of a sensor being on or off, right? On means I take an observation, off I don't take an observation. So duty cycle is basically the percentage of time for which I'm on. Okay. So what this quantity is measuring is the following. So again, I'm looking at conditioning on the change having happened at time n. I stop after time n, so I'm conditioning on tau bigger than n. And then I'm looking at the average number of observations that I've taken, or the duty cycle in that range from 1 to n. Okay? And I want this quantity to be small, right? So I want the largest value that it takes to be small. But I can't use the supremum of this quantity, unfortunately. And the reason I can't use the supremum is because if I look at the first time step, I have to take the first observation. There's no reason for me to skip the first observation. So if I take that first observation, then the average duty cycle at time 1 is going to be 1. Okay? And that's the largest value that the duty cycle can take. So that's why we replace the soup by the lim soup. Okay, and that's a reasonable quantity. The lim soup is basically is the largest limit that this sequence can take, and that you're really looking at the situation when you stop, where your change happens at a distant time in the future, and that's when you're most interested in saving energy, right? It's when the change happens rarely, and you're wasting a lot of observations by taking observations when you're operating the pre-change mode. Okay, so you can actually extend both formulations, Pollock and Lawrence formulation. By adding this PDC constraint. Okay. All right. So and then what about the algorithm? So that was a formulation problem. And let's go back to the Shearer algorithm. When we didn't have an observation, we updated the statistic using the prior. So what do we do now when we don't have a prior? Okay. So let's look at the evolution of the Q-sum algorithm. So what the Q-sum algorithm is doing is every time the statistic falls below 0, it gets zeroed out, right? And so why is the statistic going below 0? It's because this quantity here, the log likelihood of the observations, was a large negative number. If it's a large negative number, right, it's driving the statistic below 0, the amount by which it's negative should give you an indication as to how likely the pre-change hypothesis is, right? So maybe you can use that information to decide how many observations to skip. And that's exactly what we do in the DEQ-sum algorithm. So maybe I should bother with the equations. The picture is better. So what we do is the following. When statistic goes below 0 for the Q-sum test, instead of zeroing it out, we use that value here, and then use a constant slope to get out. Okay, so it mimics the prior in some sense in the Bayesian setting. So you go out with a linear slope, just like in the share version of this test, and basically the number of observations skipped is basically given by how negative this for a fixed slope parameter is, it's determined by how negative the undershoot went. and to avoid waiting too long before taking observation, we might want to threshold that value below to some value negative h. So you don't allow the statistic to go below that. So instead of 0 now, we have another threshold minus h, but between minus h and 0, we skip observations. Okay, and this turns out to be very good. Okay, and you can. Slope is just a parameter that we pick now to meet your pre-change duty cycle constraint. So now we have 3 parameters. We have h, d, and the slope. And we can choose these to meet the constraints. Okay, and you can actually show that this is asymptotically optimal. Right? And so you can show, first of all, you can actually show that it's very easy to show the false alarm rate is going to be smaller, because actually the data efficient test is always going to stop after the test that uses all the observations. But more importantly, you can actually show that this is actually much stronger than this first order asymptotic optimality. You can show that the difference between the delay for the data efficient test and the original Q-sum test can at most be some constant. Okay. And again, one can choose. You can actually you can choose a constraint on the PDC using these parameters mu, the slope and the negative h parameter, independent of the upper threshold. Okay, this is roughly how that behaves. It's not that hard to show. You can get a much better approximation than this, but this is a pretty good approximation. And the false alarm rate is controlled primarily by d. I don't know why this should be little d. Sorry, little d equals negative alpha. Alpha again gives you the same constraint as before. Okay, so how does this work in practice or in simulations? Well, again, this is for 25%. Sorry, this is 50% of the observations, 25% of the observations. Okay? You take a hit in the delay, but you save a lot in terms of observations prior to the change. Again, compared to fractional sampling, you get huge gains. Okay, so now it's 10 minutes to 3, so I could try and do the demo now, or do you want to? I have some slides that try and see what happens in the distributed sensor setting. Should I do that first, or? Maybe I'll go over these slides quickly in 5 minutes. I'm supposed to finish at 3, or have a little time after 3?
There's a demo that.
It's a very simple demo. It won't take too long, hopefully.
Many people have to run out at 3. Yeah.
Okay. So if you can wait for a few minutes after 3, I'll finish these slides and then I'll do the demo. Okay. All right. So what happens in when you have multiple sensors? So you look at the distributed sensor setting. Okay. And now you have sensors collecting information about some change event. They're sending information to some fusion center, and the final decision about the change is made here. Think about a bridge with sensors on it, and then the data is sent to some fusion center, and a decision about whether to stop traffic on the bridge is made by this fusion center. Okay. Now we're going to assume a querying model where the fusion center might be allowed to query the sensors to take observations. Okay. And then we'll also consider a setting where the sensors can act autonomously. Okay. And this problem of controlling these observations at the sensors in this manner is actually a special case of an area that's actually growing in popularity these days of controlled sensing for various inference applications. So rather than, and typically when you talk about detection, estimation, tracking, you don't control the sensing process, and you just take whatever data you get. There's usually no feedback that goes to the sensors. But now actually, traditionally there hasn't been. But I think now people are talking more about how you control the sensing process to give you the best data for inference. Okay, so this is a special case of that problem. Okay, so you can actually pose this problem as a dynamic programming problem, and you have to control multiple sensors, determine which ones have to be on and off, and you get a complex multi-threshold structure. And this was something that was done by a PhD student at IISc in Bangalore and his advisor Anurag Kumar. But what we wanted to do was to see if we could use the test we developed in the single sensor setting to get some good tests in the distributed sensor setting, and also try and prove asymptotic optimality if possible. Right? So, so basically, what we have in the multi-sensor setting is you still want to trade off delay versus false alarm at the fusion center, but you may have an individual PDC constraint at each sensor that you want to meet, okay, based on how, the energy available at the sensors. So we tried two different approaches, again, very simplistic at this point. One is just to serialize the DEQ sum algorithm that we had before, the data efficient Q sum algorithm. So in the serialization process, what we do is we allow the fusion center to query the sensors. So it thinks of the observations from sensors as actually over space. You can think of them as putting them serially in time instead, and then just run the data efficient algorithm on that sequence. So you basically take a vector and make it into take an n-dimensional vector with the n sensors and make it into a single dimensional sequence and run the data efficient algorithm on it. So that's one option. The other option is to run a data efficient algorithm each sensor in a distributed manner, basically, and then whatever observations end up at the fusion center after this is done, you use those to make the decision at the fusion center. Okay, so those two options we tried. Okay, so I described this already in words. So one comment about the serialized DEQ sum is that by construction you're going to meet the same PDC constraint at each sensor. Okay, whereas the distributed algorithm is a little more general. So again, basically, if at some point you've taken a bunch of sensors and observations from the sensors, statistic goes below the threshold, you skip the next few sensors basically, and then wait for the statistic to go above the threshold again to start sampling the sensors. Very simple. Okay, and the distributed algorithm is also very simple, right, to understand. So how does it work? Well, the serialized DEQ sum regs does really well. Okay, it's almost it behaves almost like the centralized algorithm that doesn't skip any observations at all. Whereas the distributed algorithm does take a hit. Again, the advantage the serialized DEQ sum algorithm has is that it has cumulative information about from all the sensors about whether the observations are the Prechange hypothesis or not. Okay, and you can really exploit that to gain a lot in terms of. But still, the distributed algorithm is still at least kind of is halfway between doing something totally naive, which is just fractional sampling. Okay, and again, both of these algorithms have the right slope. You can actually prove that. That's not that hard to prove. Okay, so let me stop there. I'll leave those things up for a minute, and I need to get my sensor out so I can do my demo. I wanted to set this up before the talk, but It'll take me a couple minutes to set it up. I hope it works. If it doesn't, we'll just give up. Right? So this, let me say something about this sensor, though. Anyone work with these modes before this? You've probably seen these modes before, right? So these are telos B modes, actually, very simple modes. But you actually can do quite a bit of programming on them. So this sensor, actually, there's a few sensors on this, but what I'm going to use on this sensor is, or on this board, is just the light sensor. And so if I press one of these buttons here, written a code so that the light sensor then computes the distribution of the ambient light in this room, okay? Just a Gaussian model with some mean and variance. So I've just done that, actually. And then I can use my phone, which if I can find it, or I can borrow Sean's phone, and I have my phone. Okay. So basically, the pre-change distribution has been programmed to the ambient light in this room, and then I'm going to program the post-change distribution using the light from my phone. So, actually, Sean, if you could hold this thing, but at just a few inches like that. Okay. So I'm now programming the post-change distribution. Okay, that's done. So now, what it's going to, what this algorithm is going to try and do is implement the data efficient algorithm to detect the light in this light from this sensor. So let me get to the flashlight and turn it off for a minute. So okay, so let me explain what this is doing here now, if it works. Okay, so you might see a red light glowing on the sensor, and those of you who use the sensor, this is just, it's been programmed here to indicate when it takes an observation. So whenever the red light glows, it's taking an observation of the light in the room. Okay. Now, what I have is a piece of code which I need to hook up this sensor so you can see what the sensor is actually doing. Okay, hold on. Give me 1 second. I need to run MATLAB. And I hope it's not buggy. No, I don't need it. I'm just using a local. Oh, what happened to my screen there? Why is this? Oh, really? Uh-oh. I didn't want to see that on the screen. Oh, I see. It's turn on mirroring? Yeah. Okay. Ah, I can see that. Okay. So DEQ sum. If it works, let's see. Okay. So now you see. Okay. So so those are the two thresholds of my DEQ sum test. Actually, the lower threshold H is not shown on the screen. So basically, when I'm below the red threshold, I'm skipping observations, and each time I go above the threshold, I'm going to take an observation. You see that I programmed it so that the KL divergence is really large, okay, between the post and pre and post change distributions, because I made Sean shine a very bright light. And so every time it gets an observation, okay, it's in the pre-change mode, so it's a very large negative log likelihood ratio. It falls below immediately and starts to climb out. Okay. Now, interestingly, if I make if I cover the sensor, then it's more likely to be in the pre-change mode, and you'll see now that it takes longer to get out of the hole, so it skips more observations. Okay. Now, if things work right, if I shine the light on this thing.
Let's go towards the screen, maybe. So you'll be in the picture as well.
So now you see it starts to go above, right? And then there you go, it detected it. So it goes above the green line, it detects it. Oops, that was very strong. Okay, so basically it's doing what it's supposed to do, and it's very easy to program. Okay. Yeah.
This goes back to the question posed earlier. If you wanted to include the fact that detected might get dark or light. Suppose you have two candidate alternative distributions, for example.
Oh, yeah.
Would it be easy to modify your test?
Yeah. You can just have a mixture test. In fact, I didn't do that here, but my student did look at those possibilities too. So right now, it's a very simple model for the pre and post change. They're not Gaussian, but we just model them as Gaussian. But it turns out, because the difference is so large, it doesn't matter how we model it. It's good for a demo. It's probably not that useful in practice. Yeah. So anyway, that's the data efficient quick exchange detection.
Thank you.
Yeah. How many questions? Yeah.
So for the case where you had the Bayesian prior, I was wondering if you thought about, instead of comparing to just random sampling, thinking about what the a fixed schedule of sampling based on the fact that you know at each time sample the probability that the change has already occurred up to that time.
Yeah, actually, I should have mentioned that. I did in the Bayesian setting. We do use the prior information in the fractional sampling.
Oh, you did?
Yeah.
Oh, okay.
Yeah. But in the Minimax setting, you can.
Other questions? Yeah. I could do one for Dan.
All right. Thank you.
And before you leave, don't forget. So next week there's a remarkable statistics workshop on Monte Carlo method.